Hey, what's up? Mrs. Thompson here, and today we're going over Gibbs free energy. Gibbs free energy has a lot to do with spontaneity. So we need to know what the word spontaneous means. So I'd like you to give it a shot. What do you think it means? All right. So I looked that up in dictionary, and it said it's done or said in a natural and often sudden way and without a lot of thought or planning. Doing things that have not been planned, but that seem enjoyable and worth doing at a particular time. Okay. Spontaneity. All right. So, in fact, I would like to be more spontaneous. I'm planning on being more spontaneous in the future. You sound like me. All right. So, here we go. What does that have to do with chemistry? Okay, so a spontaneous process is something that takes place naturally without any outside intervention. So as long as you keep it at that temperature, ice is going to melt. So ice turning into water is a spontaneous process. No one has to help it as long as it's at a temperature above 0 degrees Celsius. We can consider a process to be spontaneous as long as after you activate it, after you get it started, then it continually occurs on its own without any outside intervention. So if I have this ball on top of a slide, if I activate it by giving it a little push, then it naturally rolls down on its own. You don't have to continue to push it, it just naturally slides down. So that's a spontaneous process in terms of the ball rolling down after it's activated. All right, on the right here you see a Bunsen burner. You do have to activate a Bunsen burner by taking a match to it and starting the Bunsen burner. That's just to add enough heat to get that reaction to start. But as soon as you start it, as soon as you activate it, it is spontaneous. It continues to occur on its own. Every year when I bring up the word spontaneous and we think about chemistry, my students often go to spontaneous human combustion. Can people spontaneously burst into flame? I want you, if you're interested, to go to that YouTube video and check it out. See if you believe that humans can spontaneously burst into flame. All right. What about this food coloring? If we take a drop of food coloring and it spreads out in a glass, I want to know, does this spontaneously happen on its own, or do you have to add some outside intervention? Remember, we're not talking about me adding drops in there, just talking about after it's placed together, do they naturally spread out? Yes, it does. It is spontaneous. You're going to write spontaneous. All right, B. If we use electricity to separate hydrogen and oxygen in water, is this spontaneous? The answer is no. It is what we call non-spontaneous. Why? Because you constantly have to feed the water with an electrical source. It doesn't stop. If it stops, then it's separating it into hydrogen and oxygen stops. No. Okay, so the burning of hydrogen gas in oxygen, is it spontaneous or non-spontaneous? Well, it does require a little bit of activation, but as soon as it gets activated, it continues to burn on its own. So hydrogen gas burning in oxygen is spontaneous. All right. So next, we're going to talk about Gibbs free energy. It has its own symbol. It is delta G, or just G for Gibbs. Gibbs free energy is the energy that is available to do work. So after a reaction has taken place, if there's any leftover energy released, then that energy can go into performing a task. If this is the case, energy is available to do work, we say that this reaction will happen spontaneously. Here you see a man trying to push a car. Normally a car should move on its own, right? There's no gas possibly left to be able to do work, so he's got to put in the work. All right, so next we have to talk about the balance between entropy and enthalpy. Delta S, entropy, delta H, enthalpy. So there is a delicate balance between these that can help us predict whether a reaction will occur spontaneously or not. All right, so reactions are processes that release energy tend to be spontaneous. So negative delta H's or exothermic reactions lend towards spontaneity. In terms of entropy, we want things that are naturally going to happen. That is definitely disorder. So if a reaction increases the amount of disorder, then it is most likely to be spontaneous. Okay, so here comes the tricky part. You know that delta H being negative lends towards spontaneity. Delta S being positive lends towards spontaneity as well. Well, what's the sign when something is spontaneous or not? Well, if delta G is negative, then it's going to be a spontaneous reaction. If delta G is positive, then it's going to be non-spontaneous. Why? Because remember, negative is a release of energy. So if there's energy released, then there's energy left over to do work and become spontaneous. All right, so you see that here in this ball rolling down the hill. This is spontaneous. It's a negative delta G, but making him push the ball up the hill, okay, him putting in the work, that is non-spontaneous. So let's clarify that. It's spontaneous because there's leftover energy to do work. All right, so there's another way to do this. There's also calculating delta G. And so to calculate delta G, you have delta G is equal to delta H minus T delta S. G stands for Gibbs free energy, H for enthalpy, not E, T for temperature, and this time the temperature has to be in Kelvin because the units of entropy are joules per Kelvin. And entropy is S. Okay, so let's try one of these problems. They're usually not very hard. We like math. All right. So here we go. For a process, delta H of the system is 145 kilojoules. Delta S is 322 joules per Kelvin. And we want to know, is this process going to be spontaneous at 382 Kelvin? We use the equation. We're going to find delta G. That'll help us determine if it's spontaneous or not. Okay. And so before we can do that, we have to convert the joules into kilojoules because you cannot take kilojoules and subtract joules. That won't happen. The units are not the same, so convert. Let's do that. 322 joules per Kelvin. What I do is just multiply by 1 over 1,000 to change the joules into kilojoules, and I get 0.322 kilojoules per Kelvin. Then I can plug it in. So 145 for delta H, 382 for the Kelvin, and the 0.322 for the entropy. The Kelvin units cancel, and so that's how you end up just subtracting kilojoules. And that is 22 kilojoules. Just rounding to places here because I'm subtracting. Put a box around it. And almost done. I figured out the change in Gibbs free energy. It is a positive change, positive 22 kilojoules. So, is this spontaneous? No. It is non-spontaneous because it's positive. You have to add energy. You have to put in work. It doesn't come out for you. All right. Okay. Not only do we have to be able to calculate delta T, but we also have to predict it based on the delicate balance between enthalpy and entropy. All right, so recall that the universe favors exothermic reaction, one that releases heat because we want that extra heat to go into doing work later, and increasing the disorder because things just naturally occur to randomness. We have to put work to make them not random. Right. If you look at the equation, you can see that temperature, T, has an impact on entropy. Why? Because it's right next to entropy. If this number is small, that makes the magnitude of this, what we're subtracting, small. If this number is big, that makes the magnitude of this part of the equation bigger. Okay. So, because of that, when the temperature is low, delta H dictates the sign of delta G. Okay. Temperature is low, delta H will have a bigger impact, a bigger say on whether it's spontaneous or not. Opposite's true when temperature is high. When temperature is high, that makes this side of the equation bigger, and so it's S that will dictate size of delta G, whether it's positive or negative. This is the battle for spontaneity table. And so in this table, we're going to go through and look at different situations to determine whether a reaction is going to be spontaneous at high temperatures or low temperatures. We're not going to talk about the specific temperature that it takes. You can actually calculate this. We're just going to state whether that's a high temperature or a low temperature. And it's different for each one. Alright, so first thing we're going to do is look at delta H and delta S and determine whether that is favored by the universe. So, a delta H being negative, is that favored by the universe? Yes or no? An exothermic reaction is favored by the universe. So you're going to write yes right there. When entropy is positive, when entropy increases, is that favored by the universe? Yeah, things become more random. Alright, so if both delta H and delta S are saying yes, then there's no battle here. Both are saying it's going to be spontaneous. Delta G is going to be negative. Okay, let's take the other extreme here in this situation. So I'm going to go to the bottom one. When delta H is positive, that is an endothermic reaction. That is not favored by the universe, so that is a no. When entropy decreases and it becomes more organized, that's not spontaneous, or doesn't lend towards spontaneity, so that is also a no. So if both are saying no, again, no battle. It's just not going to be spontaneous. And if it's not spontaneous, then the sign of delta G is going to be positive. Okay, so in these two situations, we either have yes or no. Yes, yes, no, no. Okay, so in the yes, yes column, we're going to say that it is always spontaneous. It doesn't matter what temperature, it's always going to be spontaneous. On the no, no side, we're going to say that is never, ever going to be spontaneous. You will have to put in work to get that to go. Just like the separation of water using electricity. It's not spontaneous. You have to continually put in work. All right. These two in the middle, we'll say, are sometimes spontaneous. Why? Because one is going to say yes and the other is going to say no. So let's see which is going to happen first. So positive delta H means that it is endothermic and that is not favored by the universe, because you have to put in some work to heat it up. And then an increase in entropy is saying yes, it's naturally going to become disorganized. Okay, so no and yes. So which one wins? Depends on temperature. So please write this. High temperature, S wins. Low temperature, H wins. Okay. Remember we talked about the magnitude of delta S because of the size of temperature. Okay. So at high temperature, S wins. So that means S will dictate whether it's spontaneous or non-spontaneous. So at high temperatures, S is saying yes. So we'll write spontaneous. Okay. In this case, in low temperatures, H wins. So H is saying no. So if the temperature is low, it is non-spontaneous. So let's try the next one. What about when it is exothermic and it's saying yes, but the entropy decreasing is saying no? Well, at high temperatures, S wins. So S is saying no at high temperatures. This is going to be non-spontaneous when the temperature is high. And then at low temperatures, we have H winning. So if H is saying yes, at high temperatures, it will be spontaneous. let's think about this one in terms of the equation. Okay, so where we're saying delta H is negative and delta H is saying yes, it's going to be spontaneous. So we ignore this part. If delta H is negative, then delta G is negative, which would make it spontaneous. Okay, so then if we throw back entropy in here, okay, if temperature is high, that makes this high. So that being no would make the no high. So high that it could overpower the delta H. Why? Because a negative, right here, negative S times this negative will be positive. Making this side bigger in terms of positive is going to make delta G positive. If delta G is positive, then it's not spontaneous. All right, hopefully I didn't blow your mind there. Hopefully this table will help you. You might want to memorize this table, get a good idea of what's going on with entropy and enthalpy and what wins and what temperatures. When is that always case? When is the never case? And when do you have to look at temperature to figure it out? So let's try an example where we have to predict whether it's spontaneous or not, and if it's spontaneous at high temperatures or low temperatures. So here we have a reaction, and because we have a reaction, there's a couple things that we can see. We can predict the sign of delta H, the sign of delta S, and then the sign of delta G. Okay. So this reaction is exothermic. I know it's exothermic because the energy is on the right side of the arrow being produced. The product is given off. So delta H is negative. Okay. Second, because gas is turning into liquid. Remember, you look at phase change first. If gas is turning to liquid, then it's becoming less disordered because gases are disordered. Less disordered means a negative change in entropy. All right. So what is going on in terms of the battle for spontaneity? Delta H is saying yes, be spontaneous. Delta S, on the other hand, is saying no, shouldn't be spontaneous. So is it? Well, it's always going to be a maybe because we've got one saying yes and one saying no. But let's figure out when is it going to be spontaneous, at temperatures that are high or temperatures that are low. So it will be spontaneous when delta H wins. Okay, when is delta H going to win? Well, we want this to be small so delta H can win. So temperature should be small so delta H can win. So it's spontaneous at low temperatures. Okay, last example. We're going to look at freezing versus melting. We know these two processes to be spontaneous. We know that they occur on their own as long as you have them at the right temperature. So let's see how that works. So in terms of freezing, I'm going from water to ice. So the other way, going that curve, from water to ice. All right, so in terms of endothermic versus exothermic, it has to release energy to turn into a solid. So that's a negative delta H. For entropy, it's becoming more ordered, so less disordered. So that liquid to solid is a negative change in entropy. Okay, this one is saying yes, this one is saying no. So when is it going to be spontaneous? When delta H wins at low temperatures. And that's true because water does form ice when it's really cold, right? Low temperatures. And that is different for every single substance, whether the temperature is 0 and that means that it's low, or the temperature is 100 and that means it's low for that substance or that process that's happening. So we're just saying theoretically should those temperatures be low or high, not the exact temperature, which we are defining low or high to be. Okay. In this case, that is temperatures below 0. All right. For melting, we're going from solid to liquid. You have to put energy in, so that is endothermic or positive delta H. And then from solid to liquid to happen, you are increasing the disorder, so it's a positive delta. All right, in terms of the universe, delta H is saying no, delta S is saying yes. Okay, so who is going to win? The battle of spontaneity depends on the temperature. So if we want temperature to dictate that, so let's see, this is going to be bigger when temperature is bigger or higher or high temperature. So it will be spontaneous at high temperatures. Okay, that's what happens. Ice melts at a warmer temperature. In this case, I will see you in class so we can work on predicting these.